Welcome to Unit 9 review. In this unit, we will take some of the concepts we have already learned about thermodynamics and expand upon them, focusing largely on the practical applications of this information.
Specifically, we will discuss entropy, Gibbs free energy, thermodynamic and kinetic control, free energy and equilibrium, coupled reactions, galvanic and electrolytic cells, cell potential, and electrolysis.
Let's start out by tackling a new concept which can be a bit difficult to grasp at first, and that is entropy.
Entropy is a term that refers to the dispersal of matter and energy. When matter and energy are dispersed or become more spread out and random in their configurations, entropy is increasing. When matter and energy become less dispersed, entropy would be decreasing. We will represent entropy with a capital S, so delta S will be the change in entropy, and this will take on a positive value for an entropically favorable process, where entropy increases, and a negative value for an entropically unfavorable process, where entropy decreases. Examples of an increase in entropy would be things like phase changes from solid to liquid to gas, heat flowing from hot objects to cold objects, or decomposition reactions where molecules split apart into smaller molecules. This would also be the case when a sample of gas has its volume increase, as particles will disperse around the greater volume, or when the temperature of a gas increases because the distribution of kinetic energies for the particles of a gas becomes more dispersed, meaning that this bell curve on a Maxwell-Boltzmann distribution gets wider. Examples of a decrease in entropy would be things like phase changes from gas to liquid to solid, or synthesis reactions where smaller molecules fuse into larger ones. We can also calculate the change in entropy for a chemical process by finding the sum of the absolute entropies of the products and subtracting from that the sum of the absolute entropies of the reactants. Now, we have already discussed the concept of enthalpy. This concept can be combined with entropy as well as temperature in order to determine something called spontaneity, which is governed by something called Gibbs free energy. In order to understand this concept, the first thing we want to do is distinguish between a spontaneous and non-spontaneous process. A spontaneous process is one that simply happens on its own, completely naturally. Imagine water flowing in a river downhill. This happens because of gravity, and it is completely spontaneous, occurring with no intervention. A non-spontaneous process is one that will not occur unless it is driven by energy input from an external source. Water flowing uphill is non-spontaneous, meaning it won't happen on its own, but with the help of a pump that can produce energy that will drive the water against gravity, we can make this process happen. We can view phase changes this way too. Under standard conditions, ice will melt, but liquid water will not freeze. One process is spontaneous, the other is non-spontaneous. We should note that spontaneity has nothing to do with how fast or slow a process is. There are spontaneous reactions that happen in a split second, and there are some that happen over many years. For this reason, we can also refer to a spontaneous process as one which is thermodynamically favorable, so keep this in mind as synonymous terminology. Also, just like with entropy, we can use Gibbs free energy of formation data for both reactants and products to determine the change in Gibbs free energy for a reaction using this equation. Now that we understand the difference between a spontaneous process and a non-spontaneous process, we want to be able to predict what will spontaneously happen within a system. Let's take, for example, the isolated system where two flasks are connected by a closed valve. The flask on the left is filled with an ideal gas, while the flask on the right is a complete vacuum. This means no matter and therefore no pressure. If the valve is opened, we can predict that the gas will spontaneously move to fill both flasks, and that once it has filled both flasks, it will not spontaneously go back to its previous state. That would require energy input. Now we have to understand that the spontaneity in this case has nothing to do with the process being energetically favorable. No work has been done by the particles of gas because the pressure of a vacuum is zero, so there was nothing to push against, meaning there was no change in the total pressure of the system. The particles are now just more dispersed. In addition, there was no heat exchanged in this process because this is an isolated system. That means the driving force of this process is the actual dispersal of matter itself. It is the case that the universe will spontaneously move towards states where matter is more dispersed. Actually, this doesn't only apply to matter, it applies to energy as well. We can look at an analogous system involving two isolated objects at two different temperatures, where X is hot and Y is cold. If these objects come into contact with one another, heat energy will spontaneously flow from the hot object to the cold object until both objects are at a uniform temperature. Again, spontaneity favors dispersal, but this time rather than matter, we are looking at the dispersal of energy. So the dispersal of matter and energy is entropically favorable and is a factor in determining spontaneity. But now we have to involve enthalpy. We know that an exothermic reaction is more likely to be spontaneous, while an endothermic reaction is more likely to be non-spontaneous. But we want to be able to confidently predict whether any process is spontaneous or not, so we need to combine enthalpy and entropy to get another thermodynamic quantity, Gibbs free energy, symbolized with a capital G. This is the parameter that will unequivocally predict whether a reaction is spontaneous, and it depends on enthalpy, entropy, and temperature according to this equation. Of course, more useful than assigning absolute values, we typically measure changes in these values, so we can say that the change in Gibbs free energy over a particular process is equal to the change in enthalpy minus the temperature times the change in entropy. This equation is invaluable in chemistry. Delta G tells us information about the entropy change for the universe rather than just for the system, which is a more definitive way of determining spontaneity. So it is the case that if the delta G for a reaction is negative, the reaction will be spontaneous, or exergonic. If the delta G is positive, the reaction will be non-spontaneous, or endergonic. And if delta G equals 0, the system is at equilibrium and any accompanying process will be reversible. So now let's go through some situations and describe whether they result in a spontaneous process or non-spontaneous process. The way we want to go about this is by examining the sign of delta G for the different combinations for signs of delta H and delta S that are possible. For example, let's say delta H is negative, meaning an exothermic reaction, and delta S is positive, meaning entropy increases. Well, a negative minus a positive will always be negative, so given these parameters, a process will always be spontaneous. This makes sense, as if something is both enthalpically and entropically favorable, it should be spontaneous. Now let's flip both, a positive delta H and a negative delta S. A positive minus a negative will always be positive, so such a process will always be non-spontaneous. Again, this makes sense, as if a process is both enthalpically and entropically unfavorable, it should be non-spontaneous. Now let's examine the situation where one parameter is favorable and one is unfavorable. Let's say delta H is positive and delta S is positive, so it's enthalpically unfavorable but entropically favorable. Well, a positive minus a positive can be positive or negative depending on magnitudes. That's where temperature comes in. If the temperature is high, the second positive will be large, and a smaller positive minus a bigger positive will become negative, and the process will be spontaneous. So under these parameters, a process will be spontaneous at high temperatures. Then if we make both of them negative, it is enthalpically favorable, but entropically unfavorable, and a negative minus a negative can be either positive or negative. This time, if t is very small, then the second negative could be smaller than the first, and a larger negative minus a smaller negative will remain negative, so a process with these parameters will be spontaneous at low temperatures. If we need to predict spontaneity on the basis of a given delta H and delta S without having to do the math, we can consult this chart which summarizes the different possibilities, whether spontaneous, non-spontaneous, or temperature dependent.
We can apply this concept of free energy and spontaneity to the process of dissolution as well, as we alluded to in our unit on equilibria. Let's combine all these concepts now.
As we recall, in order for something like sodium chloride to dissolve in water, the individual ions must become solvated. That is to say, the ions must separate from one another, leaving the lattice, and become surrounded by water molecules so as to generate ion-dipole interactions. The positively charged sodium ions will interact with the negative end of the net dipole on a number of water molecules, and the negatively charged chloride ions will interact with the positive end of the net dipole on a number of water molecules. This is what prompts dissolution, because the system would be moving to a much higher energy in breaking the ionic bonds and pulling all the ions apart. That is to say, the lattice energy of the ionic solid is lost, and must then be accounted for by the hydration energy, or the energy released when the ions generate all of these new interactions in solution. We have already learned about the Gibbs free energy equation, delta G equals delta H minus T delta S, where delta H is the change in enthalpy and delta S is the change in entropy. And we know that a negative value for delta G will correspond to a spontaneous process. Of course, we also know that sodium chloride dissolves spontaneously in water. Anyone can demonstrate this for themselves in the kitchen, so this process must have a negative delta G value. The question is whether the spontaneity is driven by enthalpic or entropic favorability, or both. Let us therefore get quantitative. The lattice energy and hydration energy of sodium chloride are tabulated values that we can easily look up. As it turns out, the lattice energy is 778 kilojoules per mole. What this means is that 778 kilojoules of energy would be required to separate every ion in 1 mole of sodium chloride, such that no electrostatic interactions are being made any longer. Additionally, the hydration energy of sodium chloride is negative 774 kilojoules per mole. This means that 774 kilojoules of energy would be released if all of the ions in 1 mole of sodium chloride were to go from totally isolated to being fully hydrated by water molecules, making as many ion-dipole interactions as possible and bringing the system to a lower energy. When we add these values together, we get the change in enthalpy for the dissolution of sodium chloride in water, and perhaps a bit surprisingly, we see that the process is slightly endothermic at 4 kilojoules per mole. The amount of energy required to disrupt the lattice is just barely more than the energy released upon dissolution, so this is not an enthalpically driven process. But recalling our Gibbs free energy equation, even with a positive delta H, if the delta S is sufficiently positive, we can still end up with a negative delta G and a spontaneous process. And it is indeed the case that dissolution is entropically favorable, as it involves a dispersal of matter. So the dissolution of sodium chloride in water is an entropically driven process. In fact, the higher the temperature, the more relevant this second term becomes, because as T delta S gets bigger, delta G becomes more negative, and this is why most soluble ionic solids have their solubilities increase at higher temperatures. But the key thing to understand about dissolution is that just as with any other chemical process, there is a change in enthalpy and a change in entropy, and both must be considered when examining the spontaneity of the process. While the dissolution of sodium chloride is slightly endothermic, dissolution can be exothermic for many other salts. It all depends on the lattice energy of that particular ionic solid and whether it is exceeded by the hydration energy.
Now let's return to energy diagrams to examine thermodynamic versus kinetic control.
Sometimes multiple physical or chemical processes are possible for a particular system. These will likely have different activation energies as well as different changes in enthalpy. The pathway that results in the lowest energy product is the thermodynamic pathway. This has the most favorable change in enthalpy and thus releases the most energy. The pathway with the lowest activation energy is the kinetic pathway. This is the fastest process because it is the easiest to get over the activation barrier. It is possible for both of these pathways to be spontaneous, but one or both could be very slow. Lower temperatures lead to kinetic control, because the system will only have enough kinetic energy to get over the lowest activation energy available. Higher temperatures lead to thermodynamic control, because there is enough kinetic energy to get over any energy barrier, so the most favorable change in enthalpy will dictate the preferred pathway. We will also want to relate the concept of free energy to equilibria by relating delta G and K, the equilibrium constant. For an equilibrium, if the forward reaction has a negative delta G, it is spontaneous, and will thus be the dominant direction of the equilibrium, with products being favored, which will correlate with a K value that is greater than 1. If delta G is positive, reactants are favored, and K will be less than 1. Mathematically, the two parameters are related by this equation, with the standard Gibbs free energy change, which implies standard conditions, being equal to negative RT natural log K, where R is the gas constant and T is temperature in Kelvin.
We have just one more major topic to discuss, and that is electrochemistry. We need to know about various electrochemical cells and be able to perform calculations that pertain to them. So let's tackle this last topic now.
We've already learned about redox reactions where electron transfer occurs, and the substance that loses electrons is being oxidized, while the substance that gains electrons is being reduced. This is actually the type of chemistry that is utilized in things like batteries, which are examples of electrochemical cells. Before we dive into electrochemical cells, let's first summarize some terms and concepts that are associated with electricity, which will make everything a little easier to grasp. First, we have to understand electrical charge, which is carried by subatomic particles. The SI unit for charge is the coulomb, and one proton carries 1.602 times 10 to the negative 19 coulombs. Electric charge will typically flow in the form of electrons or ions, and the rate of charge flow is called electric current. The SI unit for current is the ampere. An ampere is equal to 1 coulomb per second, so in this way, electric current can truly be considered a rate. A current will always flow in a path called a circuit, which is typically a closed path. The charge flow itself is generated by an electric potential. This is the ability of the electric field to do work, and it is measured in volts, which are joules per coulomb. This means that when 1 coulomb of charge moves through a potential difference of 1 volt, it generates 1 joule of energy. And lastly, it is the presence of electric charge in the form of these various particles that generates an electric field in the first place. We don't need to have a sophisticated understanding of this physics terminology, but we will be using these words frequently, so it is a good idea to at least know their definitions. Now we are ready to examine electrochemical cells, which couple redox reactions with an electrical current. A galvanic cell, also called a voltaic cell, is a kind of electrochemical cell in which a spontaneous redox reaction is used to generate an electric current, and we can harvest that electrical energy to use for our own purposes, such as in a battery. In a galvanic cell such as this one, we can split things up into an oxidation half reaction and reduction half reaction, which are physically separated so that the resulting current can flow through an external wire. Each beaker is called a half cell, and each half cell will have a metal electrode. The one that is made of the metal to be oxidized, in this case copper, is called the anode, and the one that contains the metal that is to be reduced, in this case silver, is called the cathode. The half cells are connected by a salt bridge that maintains charge balance. Here's how this works. Copper atoms in the anode are oxidized, and in the process they become copper ions, which will fall off the electrode and enter solution. To maintain charge balance, nitrate ions leave the salt bridge and enter the oxidation half cell. The electrons from this oxidation travel through the wire and arrive at the silver cathode. Here, silver ions from the solution in the half cell will accept the electrons and become neutral silver atoms as they deposit onto the electrode, joining the solid lattice. To compensate for the loss of positively charged ions, negatively charged nitrate ions leave solution and enter the salt bridge, while sodium ions enter the half cell from the salt bridge. This is how each half cell remains electrically neutral, which is what allows the cell to conduct electricity. So without the salt bridge, this wouldn't work. When everything is connected, the cell will have a cell potential. This is the energy available per unit charge from the redox reaction, measured in volts, which is joules per coulomb. Next, we need to learn the shorthand that we use to communicate the materials that are involved in any galvanic cell. For example, how would we use writing to describe this particular galvanic cell? That would look like this. The left half will describe the anode. We list the material in the anode first, which is solid copper. The vertical line represents a phase boundary, which is the one between the solid electrode and aqueous solution. And then we describe the anode solution, including concentration if known. Then there is a double vertical line, which signifies the salt bridge. This separates the anode from the cathode. Then we describe the cathode solution, in this case silver ions, along with concentration. Then there is another vertical line to signify the phase boundary between the cathode solution and the cathode itself. And lastly, the material in the cathode, which is solid silver. Let's note that spectator ions are not listed. Those are the nitrate ions and sodium ions, and the simplest form of each half reaction is shown, so all the coefficients are 1. Let's try one just to make sure we can write in cell notation. Here is a redox reaction. What is the cell notation that describes the galvanic cell that utilizes this redox reaction? Well, first let's recognize that this would be the oxidation half reaction, and therefore this is the anode. This is the reduction half reaction, hence this will be the cathode. So let's use the simplest form of these half reactions to construct the cell notation. We have the chromium anode, the anode solution, and on the other side of the salt bridge there's the cathode solution and the copper cathode. Now we need to know how to perform calculations associated with galvanic cells that will tell us precisely how much current will be generated. This will involve looking at reduction potentials. Let's bring back our galvanic cell involving a copper anode and a silver cathode. This particular cell has a cell potential of 0.46 volts, which is generated due to the difference in the electrical potentials for each electrode, and it is specific to these materials, copper and silver. A different combination of anode and cathode would result in a different cell potential. So we should have tabulated information in order to know what the cell potential would be for any hypothetical pairing of anode and cathode. The problem is that we can't really list potentials for isolated materials without context. We need some kind of reference. That's why we use the standard hydrogen electrode. This is a platinum electrode sitting in 1 molar hydrochloric acid that facilitates the reduction of hydrogen ions into hydrogen gas, and we say that this has a standard reduction potential of 0 volts. Now we can list everything else in reference to this electrode. Let's say we create a cell by combining the standard hydrogen electrode with a copper electrode. Now we can measure the standard reduction potential of copper. In this case, the hydrogen electrode is the anode and the copper electrode is the cathode, and we see that this generates a cell potential of 0.337 volts. If cell potential, or E cell, is given by E cathode minus E anode, and E anode is the reference electrode of 0 volts, then the reduction potential of copper is all of the 0.337 volts. We can do this with any material. Let's replace the copper cathode with a silver one. Now the voltmeter reads 0.8 volts, so that must be the standard reduction potential for silver 1 ions, because again, the reference electrode will be 0. This method has been used to determine the standard reduction potentials for many materials, some of which are listed here. With these values tabulated, we can just refer to them if we wish to calculate E cell for any hypothetical galvanic cell. We simply use the equation E cell equals E cathode minus E anode. Just plug in the standard reduction potentials for any two materials, and we can easily calculate the cell potential for the cell that would result when we put those two materials together. For example, a cell with a copper anode and a silver cathode will have a cell potential according to this equation. We just take E cathode, in this case silver, and subtract from that E anode, in this case copper. The tabulated standard reduction potentials for these materials, as we saw earlier, are 0.8 volts for silver and 0.34 volts for copper, so we will get 0.46 volts. This agrees with what the voltmeter says if we create such a cell, so we can see that we don't have to physically set up a galvanic cell in order to predict the cell potential it will have. We just have to use the tabulated reduction potentials and do the arithmetic, and we have such values for any material you might want to use. One point we must understand is this. Since all substances are listed in terms of reduction potentials, we must know which substance is going to be oxidized and which will be reduced. For example, let's say that we were to construct a cell from gold and nickel, and we want to identify which will be the cathode and which will be the anode, and we want to calculate the standard cell potential. We can simply refer to their standard reduction potentials. Gold has a positive value for this, which means that it is a favorable process, while nickel has a negative value for its standard reduction potential, which means that it is less favorable. So gold, being the more positive value, is the one that will be reduced, so this is the reduction half reaction. Meanwhile, nickel must therefore be oxidized, so this is the oxidation half reaction. This also means that gold will be the cathode and nickel will be the anode. Now that we have determined which is which, we can plug the associated reduction potentials into the equation for E cell. Now, it may seem unintuitive, but we actually do not have to modify these values whatsoever, not to compensate for the direction of the reaction, and not even for stoichiometry associated with the number of electrons. We simply plug in the numbers precisely as they are in the tabulated data. And if we do this, we get E cathode minus E anode, and this will give us 1.755 volts as the standard cell potential. So to summarize, it is easy to calculate cell potentials for any hypothetical galvanic cell. First, we simply look up the tabulated standard reduction potentials for the two substances we are curious about. Then we figure out which of the two substances will be the cathode and which will be the anode. Again, the one with the larger or more positive standard reduction potential will be the cathode. Then we just plug them into this equation precisely as they are to get the answer. Now, galvanic cells are not the only type of electrochemical cell. Remember, with these, a spontaneous redox reaction is used to generate an electric current, which can then be utilized to power electronic devices. Another type of cell is called an electrolytic cell. In direct contrast with the galvanic cell, this is a cell in which an electric current is utilized in order to drive an otherwise non-spontaneous redox reaction. Let's look at water to see an example of electrolysis. Water is a stable molecule. It does not spontaneously undergo a redox reaction to become hydrogen gas and oxygen gas. But if we put some electrodes in water to form an electrolytic cell, electrons from the current that is generated can facilitate this chemistry, and water molecules will indeed split up into hydrogen and oxygen molecules. So the same principles of oxidation and reduction and electron flow that are present in galvanic cells also apply in electrolytic cells. The two just run in opposite directions, one from chemical energy to electrical energy, and the other one from electrical energy to chemical energy. Another example of an electrolytic cell is the type of battery found in an electric car. The battery charges up when plugged into a source of electricity and can then be used to power the car. Now that we know the definition of an electrolytic cell, let's look at an example of an electrolytic solution to see exactly what is going on at the anode and cathode. First, let's examine the electrolysis of molten sodium chloride. Here, electrons from the current go and reduce sodium ions in solution, which then deposit onto the cathode. Chloride ions then oxidize as they deposit onto the anode. Of course, this is a non-spontaneous process, so it will require a minimum of 4 volts in the way of a supplied electric current to occur. We can see why this is the case if we look at the half reactions associated with this cell. The E cell for the overall reaction is negative 4 volts, and this is why this is the minimum voltage that must be applied in order to drive the reaction. We can also correlate cell potential with Gibbs free energy via this equation, where the standard Gibbs free energy change equals negative NF E cell. Here, n is the number of moles of electrons being transferred, and F is Faraday's constant, 96,485 coulombs per mole. This should make sense, since a positive cell potential means a spontaneous redox reaction, such as that found in a galvanic cell, and this negative sign will therefore produce a negative delta G, which also correlates with spontaneity. A negative cell potential means a non-spontaneous redox reaction, like that found in an electrolytic cell, and the negative sign will produce a positive delta G, which also correlates with non-spontaneity, hence the need for the application of an electric current to drive the reaction. We will also want to touch upon cell potential for cells that are under non-standard conditions. Tabulated cell potentials are collected under standard conditions, so if parameters like concentration are non-standard, we will need to use something called the Nernst equation to do calculations. This says that cell potential under any conditions will be equal to cell potential under standard conditions minus RT over NF times the natural log of Q, the reaction quotient. As always, R is the gas constant in joules per Kelvin moles, T is the temperature in Kelvin, and then we have moles of electrons and Faraday's constant. What this tells us is that the cell potential depends on the reaction quotient of the reaction. As the forward reaction proceeds and reactants are consumed, products will form, and the reaction quotient will increase. As a result, the cell potential will gradually decrease until equilibrium is reached.
And with that, we conclude Unit 9 and our review in general for the AP Chemistry exam. Hopefully all of these important concepts are now much clearer in your mind. Be sure to check out the database of practice problems so you can apply your new understanding and prepare for the precise types of questions you will be asked on test day. Best of luck!